Hello, this is session 23, page 358. Normally you'd be doing this by yourself. I thought that since we have kind of limited time together here, that I might give you some background for it, do a few problems just to show how to go, so that when we get to the next session, session 24, there won't be too many questions, at least on this, so we can proceed to talk about that in our conferencing. I want to go through a few of the formulas first with you before we look at the particular page, page 358. The first formula is for the relationship between radians and degrees. What I have here is the circle, unit circle, it's called, with radius 1, and proceed to write down the formula for the circle, the circumference of the circle, 2 pi r. And since we're talking about the radius is 1, actually the circumference would be 2 pi. And in addition to that circumference being 2 pi, realize that the entire circle is at 360 degrees. So basically, our circumference is 360 degrees, or 2 pi. If you divide both sides by 2, you basically get pi equal to 180 degrees. And what happens here is we have a relationship then, maybe a conversion factor we can call it, where we can say that there are pi radians per 180 degrees, or the reverse of that, there are 180 degrees for every pi radians. Basically, if these are the same, we're talking about this being 1, aren't we? If we replace the pi radians here with 180 degrees, 180 over 180, 1. If we replace the 180 degrees here with pi radians over pi radians, we also have 1. So basically, that's a little conversion factor we'll use a little bit later on page 358. We also have two other formulas, one for the area of a sector and the other for the arc length. The arc length is a portion of the curve, so it's a portion of the circumference. So what we'll say here is that what we like to do is to say, here is our formula, c equals to 2 pi r, and I'll change that c to s. I really like this better, arc length like this, because L standing for length and arc for a little arc there, but no one else wants to adjust to that symbol, so I guess we're going to be using s instead. And what we'll say is that this arc length is a portion of the circumference. Some portion, some number of degrees out of the whole circumference out of 360 degrees. And of course, if we reduce the 2 and the 360 there, we get x pi r over 180 degrees, if in fact x is in degrees. If we want to talk about x in radians, then because we talked a bit back here about the fact that pi and 180 are the same, we basically eliminate those, and we change the x to a theta there, and say that s equals to r theta, or theta r, either way, when theta is in radians. So this will give us the section of that circumference called the arc length, either here in terms of degrees, maybe I could put a little degree symbol right there, in terms of degrees, or here s equals to r theta, or theta r in terms of radians. Now the area of the sector is the area of a portion of the circle, actually a portion of the area of the disk. The circle is this ring type figure with nothing inside it. When we talk about what's inside it, then we call it a disk, you know, a CD, for example, a compact disc, or maybe a pizza type situation, a disc like that, okay? Food is always great to talk about here. So we're talking about this little piece of pie, if you would, okay? What's the area of that piece of pie there? And the area of the circle, of course, is pi r squared. And then we can go ahead and say that if we're talking about a portion of that circle, then we'll do the same thing we did back in the arc length. We'll talk about a portion, x number of degrees out of 360. And this will be the very simplified version of the sector, the area of the sector, x pi r squared over 360. Again, if we're talking x in degrees. If we like to talk about x in radians, then I'll proceed to change this 360 to 180 times 2. And then basically the 180 in pi, as we saw back before, is reduced to 1, and we're left with x r squared over 2, or again, x being the radians. We use theta instead. By the way, theta is just a Greek letter. I'll spell that for you, by the way, Theta. Theta is a Greek letter, and nothing more than just as any other letter might be, A, B, C, and D in our alphabet. It's just another letter we use. Sometimes we use others called alpha and gamma too. These are the Greek letters that are used often. Nothing more than just another letter, okay? Don't make it difficult there. But what will happen here is there's a 1 understood up top side here, and we'll change the x maybe to theta there, and say 1/2 theta r squared. And that should be our formula then for the area of the sector here in terms of radians, okay? So those are our formulas. We're going to proceed then to play with some of the geometry first. The author asks us in the first few problems there to look at supplement and complement. We'll go back and review your geometry there. And then we'll look for some of the situations of arc length and or area. And also, we're going to talk about the standard form rotations of, in terms of trig. We're getting into the trigonometry here in just a moment. So look at that too. And I'll ask you to make sure that you have your trig foundational data. I just updated that on Canvas in the files. So you should find it there. It's trig foundational data. Very, very useful for us. In fact, very useful for the test also. Has all the formulas you'll need for this particular chapter on trigonometry, okay? So good to download that, to print that off. I have mine in pink again. I unfortunately was not able to give you those. I have some nice handouts that are already made out for you, but can't give them to you because you're not here. But they are available on Canvas files, okay? So what you're looking for is called trig foundational data. And it has the standard form initial array and terminal array for what we talk about in trig, as well as the triangle there. I tend to use the x and r and y configuration instead of opposite, adjacent, hypotenuse, but I have them both listed for you here. And in fact, I kind of hold off on this and talk about this in the next session when it's really appropriate. But just to show you that it is there for you, has the formulas here, as well as arc length here, in terms of, yes, s equals to r theta, and also r squared theta over 2, the area of the sector. So we have the law of sines and cosines there too, which we won't be using in the class. We're going through various sections that the university says that every Math 104 should cover, so I'm just doing what's required there. And then the next page is the graphical analysis, a bit of that. We will not be talking about the linear or angular velocity either. And the last page is really nice. That's, again, this is back to back. Yours will be single sheeted unless you copy it back to back. The last page is the sine, cosine, tan functions as pictures, as graphs there. Really nice to play with them. Sometimes nice to do it in terms of the algebra, but also in terms of the geometry of the picture. And your author tends to stay with just sine, cosine, tan, and not the other three functions, the cosecant, secant, and cotangent. So we'll just restrict ourselves to sine, cosine, tan. We're starting with, but that again will be for session 24. Right now we're looking at session 23 and page 358. And I'd like to try a few problems with you. First, number 5 here. Number 5 says that 89 degrees is our angle, and we like to find the complement and the supplement of this angle. Going way back now to the geometry situation. The complement, you remember, hopefully, is the angle added to this angle, which makes 90 degrees, and the supplement makes 180. So for the complement here, we're talking about a 90-degree angle. If we already have 89 degrees there, then there's one more degree, isn't there, for the complement? So complement is 1 degree there. And then for the supplement, we look at it this way and say 89 degrees might be in here. And then how much more for this to make 180 degrees? And to make 180 degrees, of course, sounds like 91 in there, okay? So these are our two answers for number 5 very quickly, very easily. How much more to make 90 degrees? Obviously 1 degree. And how much to make 180 would be 91. Two answers for number 5. Number 8, the author says, here's a formula, s equals r theta. Doesn't tell you too much about it, but there's a formula that, of course, we just saw as the arc length formula. It says, look, if we're given the information there that, for this number 8, that r is 6 inches and s is 1 inch, how about going ahead and finding theta? So we'll say, in this case, s is 1 inch, and r is 6 inches, and there's theta. Basically, divide both sides by 6 inches, you're left with 1 over 6. The inches will cancel, and this is then in radians. Radians are unitless measures, if you would. So we're talking here about 1/6 of a radian. You could probably divide that, and I think it becomes maybe 0.1666, 1.17 if you like, but that's good enough for us. It's a good answer as a fraction. No need to, since we're not using this for some other table or anything else, there's no reason to change to a decimal. So we can kind of leave it at that. That's a good answer for number 8. Number 13. 13 next. 13, we're looking for 30 degrees in terms of radians. And unfortunately, I didn't write the formula there, or the conversion factor on the board for you. But we can get that back very quickly. To convert that, we have two options. Either the 180 degrees for every pi radians, or the other one, that they're pi radians for every 180 degrees. Obviously, if you multiply by this one, you can see that we're not going to cancel the degrees. It's going to be degrees squared instead, degrees squared of a radian. So we really don't want this one. What we like to do is to reverse that and use the other one, okay? Either way, it's 1, whether you talk about 180 degrees over the radians, pi radians, or pi radians over 180 degrees. So probably better to use the one that's going to reduce our degrees and say, look, they're pi radians over 180 degrees. And the degrees will then cancel for us. And basically we're left with 30 and 180. Probably get rid of the zeros at that point. And also 3 into 18 is 6 times. So how about saying pi over 6 radians? Okay. Pi over 6 radians should be a good answer for us for number 13. Again, there's no need to change this. I would presume the author's, these are odd ones so you can check the back. I presume the author will leave it at this. You could change pi to 3.14. 3.14159 keeps going on and on there. And divide that by 6 and get a decimal there, as we could have done back in number 8 also. But again, I think that's fine, leave it as a fraction there, and the author would probably agree on that, pi over 6 radians. But even if the author changes it to this, go ahead and do it either way. It doesn't really make much difference. The pi over 6 is kind of useful though. Since pi is an approximation, 3.14 is an approximation of pi, better to leave it as pi over 6. That's the exact answer, okay? So leave it there. That should be a good job for number 13. After that, try 25. Now 25 is negative 210 degrees. We'd like to change this also to radians. I'll give you 2 examples here because of the negative. It gives me a chance also to explain the negative rotation. In the trig, which we're going to talk about in the next session, and get into it a bit here in this with the rotation. The counterclockwise rotation is the positive rotation, and the clockwise rotation is negative, okay? So we begin at the initial ray or initial side is the positive x-axis, and we rotate counterclockwise to what's called back here somewhere the terminal side. So initial side here at the positive x, and terminal side somewhere in the axes here, the coordinate axes. The rotation counterclockwise is positive, rotation clockwise is negative. So for 210, we're going to go in the negative direction, this direction. We don't need that quite now. All we need to do is do what we've done before here to change from degrees to radians, but it gives me an opportunity to talk about the negative degrees. And also in the geometry, we never talked about more than 180 maybe, because of the triangle being 180. And the trig, we go as high as we want here. So in fact, positive and negative as high as we want. Let's go and do the same thing we did in the previous one. How about pi radians per 180 degrees? And then again, the degrees will cancel. That's an idea that we've done a good job there. And probably these zeros also. And I think we probably get, looks like 3 goes into both of those. 3 into 21 7 times. And don't forget your minus sign there. And 3 into 18 goes about 6 times. So it looks like 7/6 pi radians should be a nice answer for us there, okay? Gets us into a bit of the trig with the rotation, but basically the same problem there as number 13, or very similar. After that, we're looking at number 33, and 33 goes the other way. I want to give you an opportunity to look at each of these going either way. 33 says, let's talk about the 3's pi radians. and we like to change this degrees. And again, we have our choice, and we're going to choose the appropriate one here instead of writing the wrong one down. How about 180 degrees for every pi radians? Okay? In that case, the radians will end up, both radians and pi will, in fact, will cancel here. So let's go ahead and get rid of both of those. Maybe green this time. Pi radians both go. And we could probably reduce that a bit if you wanted to before we proceed. How about maybe reducing this with a 2 at least? I think 2 will work. How about 90 and 2 there, okay? Or maybe even 4. I think it's 4 will work too, won't it? Let's give 4 a try, okay? How about 4 into 8 twice? And I think 4 was in 180, 45 degrees, or 45. I should put the degrees too, I guess. There we go. 45 degrees. So what we're looking at is 3 times 45, 135 over 2. And 135 over 2. And we could divide that in probably, what, 67.5 degrees, I think, on this. 67.5 degrees. Do the arithmetic on that. Check to see if that's true. 67.5 degrees should be a nice answer for us for 33. After that, moving on to 43. 43 gives us 4 radians. And again, there are the same conversion factor, 180 degrees for every pi radians. At this time, the pi's don't go. We'll keep the pi there and save it for later to eat. And the radians will go though. And if you wanted to, we could probably change pi to 3.14. We could probably do it now or do it later. It doesn't make any difference. But we'll say that when you multiply these two and then divide by 3.14, that should be a nice situation for us. I think that's going to be 4 times 180, 720. I think that'll work. How about 720 degrees? 720 degrees divided by pi. And as I say, we'll call that pi 3.14. And let you do the division on that. And when I do the division, I get about 229 degrees. I probably use 3.1, or even if you just use 3, that'd be good. But I think 229 should be fine. Again, not expecting you to do a lot of arithmetic on this. If you want to use 3, that'd be no problem, okay? But get a good answer. If I was giving you a test on this, I'd give you the answer is 229, and maybe another answer is 150, or maybe negative 300, or 400 degrees positive. You know, something that's way off so that only 229 would be the appropriate answer. I wouldn't give you an answer like 229.1, 229.2, and 229.3 and say choose one of those. The answer would be right there or be way off, okay? So again, not asking you to give me something that's accurate there. Pi is an approximation anyhow, so just asking you for an approximation, okay? After this, we'll take a look at page 62, but I've kind of run out of space here. Maybe I can go ahead and put 62 down here and then save over the space. Let's try 62, okay? 62 says negative 450 degrees. And this time we're not being asked to go ahead and change that to radians, but being asked to say, state in which quadrant or in which axis the angle measured center position would lie. It gets us back to what I talked about back here, okay, the rotation. So if we're talking the negative rotation, we're talking going this direction here, negative, the clockwise direction, and we're going here 360 degrees for one rotation. If you subtract 360 from this for just a moment, it looks like we're going to be left with 90 degrees. So we'll proceed from here after we've gone 360 a little bit further, maybe into there, to be the total negative 450 degrees, okay? So here's negative 360 once around, and then 90 more would be our negative 450. And where are we at 90? Well, we're right here, aren't we? And that's the negative y-axis. So the question was, is this going to be on the axis or is it going to be in some quadrant? In this case, it's called quadrantal. So we say instead that it's just on the negative y-axis, okay? So the negative y-axis should be a good answer for us for number 63, okay? 62, excuse me. 62. We're looking after that at 72 and maybe 82 and I think 92. trying to get you some even problems, which are similar to the odd ones you'll be doing. So let me get rid of this first, and after we get rid of this, we'll play with 3 more problems, and then say we've kind of finished that off. Hoping that this will give you a nice intro to what's going to come later with the trig. The next few, I think, require knowing the formulas that we talked about initially here. And that's the reason I spent some time going through the derivation of the formulas. So you can use them here without necessarily saying, well, what are those all about? And we've talked about them already, so you know what they're about. So once we get to the problems, you should just be able to apply the formulas. Okay, on to 72. 72 probably carries over to 359. And 72 says that we like to go ahead and determine the angle of the smallest possible measure, which is coterminal with this particular one. Coterminal with negative 187. Coterminal means, co means together with, and terminal means ending. So we want to talk about the angle that is the same ending point. And we're talking about negative 187 here, negative 187, yes, negative 187. If we talk about negative 180, that's going to be right to there. And then, of course, we're talking about 7 degrees into this quadrant, right? 7 degrees into here. And we haven't identified these yet, but you should understand that we're talking about the x, y coordinate axes, the first quadrant, second, third, and fourth. So in the second quadrant there, we'll be talking about the sine, cos, and tan in the next session in each of these quadrants too. But to answer the question here, we want to know what's the angle that is coterminal, has the same ending. Well, if we start here and proceed to that point, you see that we would go entirely 180 degrees to get to the purple line here. 7 degrees short of that, how about 173, okay? 173 degrees, and then that's 7 more. I think we'll do a good job. It'll be the same ending point, you know, to get us down to here. 173 and 7 more is 180. So we're 7 degrees into here, just eliminate 7 from the 180. And 173 degrees should be our answer there. That's going to be the angle that's a positive angle that is coterminal, has the same ending ray, if you would, as the negative 187. After that, 82, I think, requires to look at the arc length. And I'm going to write that down for 82. Arc length formula. As soon as someone tells me to write something down, I'll say, look, what's the formula for it? Do I have a formula? And again, I would encourage you to download this trig foundational data, please. Extremely useful for you. It saves looking through the book for all the various formulas. It's right there. All the formulas you'll need from here on out through the entire semester and through the final are useful there. You can use that in the final also. For 82, 82 says to find the exact length of the arc made by the indicated information here. Okay, so 82, the radius is 6 yards and the theta is pi over 8. So 6 yards for the radius and pi over 8 for theta. And basically that's all there is to it. Just a matter of writing the formula down, inserting the data. I'd ask you probably to reduce this 6/8 to 3/4. So how about S equals to 3/4 pi yards, okay? A nice answer for us for number 82. Just by using the formula S equal to r theta that we derived initially. And lastly, number 92, kind of a short session today because it's after the test and just a few problems I would ask you to do it at home on your own. 92, it says to find the area. Find the area for 92, and this time I think 92 we're given degrees, aren't we? So we have two options here, and we want to find the area of the sector. Let's use the option involving the degrees. Again, I'll put down both here. x pi r squared over 360. That's our formula for following degrees. If we're talking about the formula involving theta, we'd say 1/2 theta r squared or theta over 2r squared. Okay, so we have two options there. And the option we'll choose is the first one because we're given degrees here. So basically, insert your degrees for x. This time 27 degrees. That's what we're given in the problem. And then the radius, I think, was given as 2.5 kilometers. So we're going to insert 2.5 kilometers here. I need a little bit of space there. And remember that back here, we're talking in 82 arc length. That's measured in units, so we're talking yards there. Here, we're talking about area, which is measured in square units. So we're going to talk about square kilometers there in just a minute. And let me finish it off though. It looks like x 70 degrees pi r squared over 360, okay? The degrees are going to go for us, and pi is just 3.4. We'll be left with kilometers squared on this. And basically, I think that the 2.5 times 2.5, 25 is 625. So probably 6.25 there, km squared. Sometimes written this way, sometimes SQ km for square kilometers. A kilometer is about 0.6 of a mile, so it's a little bit over a half mile there. The 27 degrees are gone. The degrees will be reduced also. So basically it's 27 pi and then 6.25 kilometers squared over 360. Could probably reduce that a bit. I think 9 goes into both of the 27 and 360. So you may want to give that a try. 9 into 27 3 times, and 9 to 36 4 times, you 40 there. That's probably all we can do. What you might want to do now at this point is to, even if you want to just call this pi 3, that'd be nice. You could do that. We could call it 3.14. It doesn't make any difference, but basically looking at 3 pi and 6.25 kilometers squared all over 40, okay? And you could probably even, if you wanted to, just eliminate the 0 and move the decimal one place here in front of the 6. Either way, kind of let you play with the rest of that. When I finish that, I get approximately 1.4. And I think it's in kilometers or maybe it's millimeters. Let me check this here. In fact, it was my mistake on that. It didn't say kilometers, it said millimeters. Okay, kilometers was 89, just above that. So let me change this back. Won't make much of a difference. But let's use the mm for millimeters squared and square millimeters then. This one, I guess. Square millimeters. Same thing here, square millimeters. And here. Okay. I did what I cautioned you about not doing, is sometimes you read one problem and then look up above to get the units. As I say, when I did the arithmetic on this, I got the area here as 1.4 millimeters squared or square millimeters, okay? You might want to check to see if that's what you get also from this. And this will complete then page 358, the exercise I want to do with you. We'll be looking at the session 24 next, and that'll carry us over and begin the trig with us. And again, you'll be needing this foundational data. I'll go through the entire page with you in a little bit more detail and show you what I've done here to try to consolidate. We have all the information we need here in 2 pages for the trig we'll be looking at for the next couple of weeks here. So take care, and we'll see you for session 24.